All right, welcome back. I hope you had a chance to work on this worksheet problem. I'm going to go through my style of solution, but again, if you have something you're comfortable with that's getting you the right answer in this kind of problem, it's probably good enough to get you through the course, and I don't really care one way or another. So in this case, we're given a volume flow rate of 50 cubic centimeters per second, and we're supposed to convert it to units of cubic meters or meters cubed per day. And we're going to use the same technique we did before. I'm going to try to multiply this by a number 1 that doesn't change. If I multiply by 1, I don't change the fundamental quantity, but it will actually change the units because of the particular strange form of 1 that we've written down. And in this case, I might start by thinking, well, okay, a centimeter, I know there are 100 centimeters in 1 meter. So since I want to get rid of the centimeters up here and put a meter upstairs, I might use the fact that 1 meter in the numerator is the same thing as 100 centimeters in the denominator, and that way at least one of the factors of centimeters would cancel. In other words, I couldn't really cancel this centimeter against this centimeter cube up here because we've got 3 factors of centimeters up here. So what I've got to do is put 3 copies of this factor here, or the shortcut way to do it, or the lazy person's way to do it, which is just fine. I encourage you to be lazy. That's another name for efficiency. It's just to cube this quantity because, I really want a meters cubed in the numerator, and I want a centimeters cubed in the denominator. So when I cube this, that means everything inside here gets raised to the power 3. 1 cubed, meter cubed, over 100 cubed, centimeters cubed. That's what that means. And now I can cancel, again, I'm going to be a little bit lazy, but if you will humor me here, I can cancel this centimeter against this centimeter cubed because this centimeter is inside a cube. So if I get rid of it, I'm really getting rid of a centimeter cubed in the denominator. I'm canceling it against a centimeter cube in the numerator over on the left there. So that's helps me out. But I've got to remember the stuff that's left that I didn't cancel is the meter gets cubed and the 100 gets cubed in the denominator. Okay, so I've successfully traded out a centimeter cubed in the numerator for a meter cubed, and now I'm going to do the same thing for the seconds. I don't want that second in the denominator, so I'm going to put another factor of 1 over here that has seconds in the numerator and days in the denominator. So the second gets replaced with days. I got to do a little bit of work to figure out what that is. In one day, how many seconds are there? Well, there's 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. So there's 24 times 60 seconds in every day. And so the numerator, again, is the same exact quantity as the denominator, so I'm just multiplying by 1, and now I can cancel that seconds against the other seconds, and the only units I'm left with are meters cubed divided by days. So now I've got to take all the numbers carefully in my calculator. What I've got is 50 divided by 100 cubed times 24 times 60 times 60. When I put all those numbers together, I get 4.32. And when I collect together the remaining units, I have meters cubed divided by day. So there's the units, 4.32 meters cubed per day. The reason I said this problem is just a step up from the one we did before in the last video is because of this cubing property. People often forget when they put in that conversion factor they need to cube it to really, so that 100 needs to be cubed in the calculation of this number. So that's just an example. Things aren't going to get any more complicated in changing units. That's about as bad as it gets. So if you can do that, if you're comfortable with it, that's fine. If you're not comfortable with it or you're having trouble, certainly ask me about it in our class meetings. So that was an example, and that's as bad as it's going to get for changing units. Let's go on and discuss something called significant digits, which is the degree of preciseness with which you are going to specify a physical quantity. Let's imagine significant digits and significant figures mean the same thing. So let's imagine I make the following statement. My height is 1.827448603 meters. Maybe I knew what my body mass index is, my BMI, and I knew what my weight was, and therefore I could calculate my height, and I did it in my calculator, and my calculator gives me lots of decimal places whenever I calculate anything, and I just wrote down without thinking the result that came out of my calculator. I want you to realize that this number is completely ridiculous. In other words, the digits that I have specified here are really, are meaningless. Let's just figure out the precision to which I am claiming to have specified my height. This is meters right here. That means this 7 right here is in millimeters. This 8 is in micrometers, or millionths of a meter, and this 3 is in nanometers. So I've specified my height down to the nearest nanometer. But if you think about me measuring my height isn't even, it doesn't make any sense down to nanometers. In other words, if I stand up straight, exactly how much are you going to press down the hairs on top of my head, and exactly when I straighten my back up or let it down, I may move up and down by a centimeter. Certainly I don't know my height. It's not even well defined to the nearest nanometer. So we've got to get rid of some of these and be reasonable. So I would claim that it's reasonable to specify my height to the nearest centimeter, right? This is meters, tenths of meters, 1/100ths of meters, and 1/100ths of meters is centimeters. So I specified my height to the nearest centimeter, and that's reasonable. You know, if I straighten up my back or slouch a little bit, I probably move my height less than a centimeter, you know, assuming we're pressing down on top of my hair. So the rule is be reasonable. Don't say a quantity to a precision that you really don't know it and it doesn't even make sense. Generally, for this class, we're not going to worry too much about significant digits as long as we're going to usually use 3 significant figures when we calculate something just to be reasonable. And so there's a whole calculus that goes on with how to specify when you do a calculation with certain numbers of significant figures, how to figure out how many figures the calculated number should have. We're going to ignore that in this course because it sort of distracts away from learning the physics. So just be reasonable in almost all cases. When you're on an exam and you're specifying an answer that you're going to put in an answer box or put a box around it, you should round it to the nearest, to 3 significant digits. And when I say significant figures, we always start counting from the left. This is the first, second, and third significant figures there. So when I've rounded, what it means is I say, centimeters is reasonable, millimeters is not reasonable. So I don't want to specify this 7 there. And so if I'm going to round to this place, because 7 is 5 or bigger, we're going to round up from a 2 in that position to a 3. So I've rounded to 3 sig figs, sometimes people say, in throwing away everything after the 2 and rounding up to a 3. Now, one of the other virtues of scientific notation is that it's easy to tell how many significant figures or digits the person intends. So in other words, here is a quantity, a distance, 3.700 times 10 to the 6th meters. Okay, so this is 3,700,000 meters if I specified it the standard way. And the claim is that whoever wrote down this number really believes that they know that this digit is a 7 and that this digit is a 0 and not a 2. This digit right here is a 0 and not a 1. Because they have been specified in this case, you didn't have to put those extra zeros after there. So if you see the zeros in scientific notation in that number that comes out in front, which has a name, I can't remember what the name is for the number in front of the power of 10, but if there are extra zeros given, we should take them at face value. So we would say this number has 1, 2, 3, 4 sig figs. Compare that to writing the same number in the standard decimal way, where we put the decimal at the end of the number. So 3,700,000 meters. The question is, how many significant figures is intended by the person writing down this number? And the answer is, it's impossible to tell, because we need those extra zeros there to tell us where the decimal point is. In other words, if we're going to put that decimal point right there, we need those extra zeros as placeholders, but I don't know if they're just functioning as placeholders or if the person who wrote it down really knows that this number is a 0 and this number is a 0 and this number is a 0 and not a 1. It's not, So that's one of the other virtues of scientific notation is you can always tell which digits really make sense and you don't need any placeholder digits. Okay, that was just, we don't really need to know anything about it. The upshot is be reasonable with significant digits. And now the final topic in this lightning quick, just touching on a few topics in chapter 1, is something called dimensionally balanced equations. And I don't remember what Giancoli calls it or how he addresses it in there, but this is something that will help us simplify things as we go on. So we're in physics, and this is certainly true in Giancoli, we're always going to write equations in such a way that both sides have the same dimensions when you look at the variables in the equations. So let's take an example. Here's an equation. Let's suppose I've watched an ant, or maybe a little remote control car, moving along the x-axis, and I keep track of every second, right? So it's 0 seconds, 1 second, 2 seconds, 3 seconds, what the position is in meters on the x-axis, right? And so I might say, well, I took the data at 0 seconds, it was at 0 meters. At 1 second, it was at 1 meter. At 2 seconds, it was at 4 meters. At 3 seconds, it was at 9 meters, and so on. And I said, well, that's great. That means you just square the number of seconds, and you get the position in meters. The problem with this kind of equation, which I would call not dimensionally balanced, because notice the dimensions of the right-hand side are seconds squared, square seconds, and the dimensions of the left-hand side are, it would be time squared, and the dimensions of the left-hand side would be distance. They don't match. They're different, and so it's not dimensionally balanced. The problem is, if you write down this equation and you show it to someone else, or if Giancoli put it in the book, there's multiple interpretations for what that means. You knew that when you plug in t in seconds, the x was supposed to be interpreted as meters, but I might read this equation and think, well, maybe if I put in t in seconds, I get x in kilometers. And that would give me, then I would say, wow, this thing is really moving fast. When t equals 2 seconds, it had moved to 4 kilometers. That's, obviously the thing is going really fast. And you would say, no, what I thought was in 2 seconds, it was at 4 meters. So we're never going to write down, Giancoli's never going to write down equations that look like this. Rather, he's going to use dimensionally balanced equations. So here's an example of a dimensionally balanced equation. There was a 1. Normally when we have a factor of 1 out in front of something, we don't write it down. There's no reason to put a 1 in front of the t squared. But if that 1 has some units associated with it, for example, here I've put a factor of 1 with units of meters per second squared in front of the t squared. And what this is telling me is that if I put in t in seconds, I'll have a second squared for the units over here. That second squared will cancel with the second squared in the denominator. I'll be left over with meters. So I know whatever number I get out for x, it's going to be in meters because the constant out in front of here tells me so. In my second example, I said maybe we put in seconds and it comes out in kilometers. So here would be a different dimensionally balanced equation that says something different. It says if you plug in t in seconds, you're going to get an x in kilometers. But notice, if you compare the left-hand side and the right-hand side, it is distance dimensions on this side and distance dimensions on this side. On the left, we have, well, x is to be interpreted as a distance here. It's a distance on the x-axis. And when I put in, I have a time squared right there, and then I've got a time squared in the denominator. They cancel out, and I have a distance unit in the numerator. So I've got distance on the right, distance on the left. That's an example of a dimensionally balanced equation. The virtue of using all dimensionally balanced equations is not just that we won't get confused, although that's primarily the reason we do it, but it's going to help us be a little bit lazy about putting in units when we're using all SI units. The idea is, Here's an equation that we'll become very familiar with starting in Chapter 2. It tells us how to compute the distance something has moved along the x-axis as a function of time t. And this x0, vx0, ax, those are all constants that go in the equation, and we'll talk about those as we go there. The important thing is I know if Giancarlo is writing this down or if we write it down in class, since the left-hand side has distance units, the right-hand side must also have distance units, even though it's not completely obvious when you look at it because it's a complicated equation. That means that if I plug in all SI units on the right-hand side, even though it's complicated, then I will get the SI units for the same dimension on the left-hand side. So I know the answer that's going to come out is a distance. If I plug in x0 in meters, and I plug in vx0, we'll find out the units for that are meters per second in SI units, t in seconds, ax in meters per second squared, and t in seconds. If I put all SI units on this side, I know I'm going to get the SI units because I put all SI units. I'm going to get the same dimension quantity. It's a distance. So if I know the answer is going to be a distance, I can just happily plug in all SI units over here and I say, oh, I know the SI units for x is meters. So I can conclude immediately that x is in meters without having to work out that everything canceled out in the right way. You'll see me doing that as we go on, so maybe that will make more sense. Similarly, that's true even if I solve for something like vx0. If I solve this equation for vx0, I get another complicated equation. If I put all SI units in on the left-hand side, I will get SI units out on the right-hand side of the same dimensions, and I know the dimensions of v are meters per second, or distance divided by time. So the SI units are meters per second. So I can happily put all SI units in here, and I'm just going to write meters per second next to the number I get out without having to work out all the units. That's only if you're putting in all SI units, but it's a substantial savings in time. Okay, I know that was a grab bag of topics for Chapter 1, but let me just summarize. We talked about dimensions, which are kinds of physical quantities, and how we measure them. Those are units, and there are lots of different units for every kind of dimension. SI units are certainly the most important for us. We talked about scientific notation. The advantages of scientific notation are you can specify huge or tiny numbers with ease, and you also know how many significant digits you're specifying. And we've talked about some of the important SI prefixes. We did some examples of changing units. They're not going to get any more complicated than the ones that we did here as examples. We talked about significant digits. The most important thing is be reasonable. Don't specify something that's going to make you look like a fool because it couldn't possibly make any sense. Generally, we're going to specify 3 significant digits. And then finally, you can count on the fact that every equation we'll use in this course is dimensionally balanced, and therefore, if you plug all SI units in, you know the thing that you calculate is going to come with the appropriate SI units. Okay, and that's the end of this video. We'll see you in the next one where we're starting into Chapter 2.